Hi everyone, welcome to this presentation on the simplest way to build resilient applications. Resiliency is not the lightest topic, so I hope you still have good energy levels on this Friday afternoon. So what we'll be talking about is a bit a new approach to how to tackle resiliency in microservices and in general in applications. I am Giselle van Dongen. I work for a project called Restate, which is one of the projects in the durable execution space. So we'll be talking about durable execution in general and how Restate fits in there and how it works. If you have any questions, you can use the QR code on the right top and I will answer them then after the talk. So this talk will be pretty demo heavy and I broke my wrist, so I will be doing it with one hand, so let's see how that goes. But let's first get into a bit of context about what we will be talking. So here is a small code snippet. This code snippet does in broad lines the following. So imagine I'm a reseller of Netflix and Prime and Hulu subscriptions, so video streaming services, and I have in my application somewhere this method add subscriptions, which lets me for a request from a user create a recurring payment and then create each of the subscriptions he asks for. So that could be Netflix and Hulu, for example. So now the first question is, how can we actually make this reliable? Or what are the possible catches here? Does anybody see a few or one which wants to contribute? Silence. Okay, so let's go a bit from top to bottom. So imagine this is a method which can be called over HTTP, a bit like an RPC call to this method. The first thing we need here is to make sure that if this service crashes due to some infrastructure failure or something, that we don't lose the requests that we were processing. So we need something like retry logic for the upstream caller, or something like a queue if we want to do async communication. So, all right, now we have at least a persistent place to get our request back. But even if we process this retry, there are some difficulties that we need to make sure that we handle them correctly. So how do we handle actually retries of the same request? We don't want our user to pay 2 times for the same subscription set and only get it 1 time. So one thing we could do here, for example, is deploy a key value store where we keep track of the payment IDs that we generated and store them together with the request ID. And then if there is a crash, we go look in our key value store whether we already did this payment and what the ID was. But so you see, slowly this is becoming already a bit more complex, right? We started with 5 lines of code and now we already need a queue and a key value store. We need retry logic around that payment. Probably we need something like cleanup of the data in that key value store to not make it grow out of bounds. And even then, we're actually only still solving the issues of these few lines of code and not yet looking at the full picture of how this interacts with the rest of our system. So there are so many more ways in which these things actually can go wrong. For example, things like race conditions or network partitions, zombie processes, but also the slightly more common things like just timeouts or an API being down. So who of you has encountered any of these things already in their life as a developer? Okay, at least somehow it's a relevant talk, it seems. So if you look at ways to solve this, often it involves a lot of different solutions for resilience of different parts of the system. So a few things you have there are, as I already showed, key value stores to store application state, maybe something like Amazon DynamoDB or Redis. Message queues for asynchronous communication, like Kafka and SQS. But also more complex systems like, for example, workflow orchestrators. Maybe you need to deploy something like Camunda to actually track where in execution you are, what you need to retry, and what already was successful. And then the last thing listed here is schedulers. So maybe I want to schedule something for later on, and I want to be sure that this gets executed no matter what. And so what you see in code bases is that a lot of the code you're writing is glue between all these different solutions for resiliency of different parts of your system. And even then, it's pretty hard to make sure you cover all the corner cases. You can always end up with a new corner case you didn't think about it, and then just send a voucher to the customer and apologize. So what you end up with is architectures like this that are hard to keep an overview of and have so many different things in different places that you're actually not anymore really sure where the problem is exactly. So one thing you see here is that to solve this issue of losing overview of what actually is happening in the system and when something goes wrong, how everything ties together, is to use observability tooling. And it's pretty interesting to see the amount of new tools and startups in the observability space in the last 10 years, more or less, since we started switching more and more to microservices. And I think one of the reasons for this is just that our systems have become fragmented and quite complex to actually handle all these possible ways in which distributed systems can fail. So I will not be talking about something that replaces all of this. This is more like the context of what we got ourselves into. But what I'll be talking about is definitely something that can help reduce the complexity and gives you a bit more of a trustworthy basis to build your applications on top of. So what are we doing today? As you all know, you have some clients, maybe they send some HTTP calls, you have your backend code, and your backend code interacts with maybe a database and some APIs. So what happens on a failure is that when this backend code, the service that runs the backend code disappears, you lose everything that was in it. You lose the state, the partial progress of what it was working on, and handling that resiliency is fully up to the developer to actually tackle. So Restate and durable execution as a whole have as a goal to give applications a extra component which takes care of resiliency, state, and communication. So which takes care of actually the complexity for which we otherwise would have needed so many different solutions. So in the case of Restate, the way that it looks is you have a component sitting in front of the backend, a bit like a workflow orchestrator or a message broker or a reverse proxy. It proxies requests through to the backend, and the backend becomes just a stateless function doing some work and reporting its progress back to the main server. And the main server is a resilient server which will make sure that that stands the test of time. So that sounds a bit abstract and a bit like magic, so I'll be showing quite some demos and a bit more information of how this works. So today I'll be talking about a few different use cases which are often particularly complex to get fully resilient and right. I'll be talking about workflows and sagas, concurrent async tasks, so racing futures, state machines, agents, and actors, and then finally also a bit about Kafka event processing. But before I start with workflows and sagas, I first want to show a small animation of how it works a bit under the hood, because it's easier to do this way than in a demo. So let's take again the same code snippet that I showed in the beginning, so the creation of these subscriptions to a set of streaming services. So what the durable execution does is it gives code built-in retries and recovery of progress. So the way that that looks is there is here this green context, which is an SDK in my plain Java service, which now is wrapping a few of these closures or calls that I do. And so the way this works is if I have a request for this function, so an RPC call, maybe I want to subscribe to Netflix and Disney, then what happens is the server writes down that this request took place, a bit like a message broker, but it will start a log for everything that this request will do. So it will forward it to the method. Then when it starts executing, every time you see ctx.run, what happens is a new item gets added to this execution progress log. So first you generate a payment ID. That payment ID is an entry in that log, meaning that this is now persisted as if I would persist it to a database. And you do that for actually any type of code execution where you feel you don't want or you need the resiliency. So Netflix, imagine now something goes wrong. How does this then actually recover? So the connection between here the restate server and the service drops. Restate sees that this request took place and that it never ran till completion. So it knows this still needs to be finished. So it sends a retry request. Once the service is back up, it will be able to handle that retry request. And then what it does is every time you see the ctx.run, it will look, can I find an entry for this action in the log? If it finds one, it will just return whatever it finds in the log. And if it doesn't find anything, then it will actually execute it. So for example, here this first one where I generate a unique identifier, I will just get the same unique identifier that I got during my last run. So it has basically turned it into a deterministic action across retries. So same for my payment, it will not execute it again. Then there's Netflix, and then finally it sees that Disney is not yet in the log, so it still needs to create the subscription, and then you have a successfully executed function. So this is, with a little animation, a bit how it works. So I can now show some demos of the different use cases that I talked about. So let's just start with running what I talked about in the animation. So I have here the same subscription service. This is a Spring Boot application. I have here the method add, which does those three things that I talked about. I can now run this. I'll run it in debug mode because for some of the other demo examples, I will use a few breakpoints. So this has started up. So now the next thing I need to do is start the restate server. So that's that component running in front of it. So it's a single binary. I only need to start up this thing and then that's it. And now it has a UI. So I can go to the UI to tell it where my service is actually running. So my service is running at localhost 9080. And what will then happen is restate will ask that service which things are running there, what is hosted there. And so these are the different services that I'll be showing throughout the demo. The first one that I'll start with is this subscription service. And so you can see which handlers are being hosted there and also what kind of request that they want you to send. So I don't know if this is big enough. I can make it a bit bigger. So in the case of this service, I need to give it a credit card, a list of subscriptions, and a user ID. So once I've registered this, I can now call it, and restate will proxy those requests. So I can go to this service, to the playground, and here send requests to my service. I will copy this over because typing is not my greatest skill today. All right. So I'll be subscribing to Prime, Hulu, and Netflix. So if we press send, then this will get stuck. And the reason for that is that I put a little problem in the code. So if we go to the invocations, you can now see that this request that I did 12 seconds ago is in a state retrying. So it has issues. If I click here, I see what the issue is. So the issue is that the Netflix subscription failed because the Netflix API is down. So it's constantly retrying to do that request until it will eventually succeed. And we can also have a look at that journal. So that is what I showed in the animation on the left. That is the progress of what was done until now. So first I created a payment, then I subscribed to Netflix, Hulu, or Prime, Hulu, and now I'm at Netflix, and there I have the issue that the API is down. So let's solve this. So in my case, it's actually just if subscription contains Netflix, then throw an exception. So if I comment this out and restart my application, then it will retry it and everything should end all right. So it can take a few seconds because it retries with exponential backup. So what you see is that now it started, it invoked my service again, and now the only thing it created was this subscription for Netflix. So it didn't redo the other steps. And this is also gone now. So that's the real life example of what I showed in the animation earlier. Let's now have a look at how this relates to sagas. Does anybody have an idea of how this could relate to sagas? No? So if you look at durable execution, in essence, what you do is you try to push execution always forward. When something goes wrong, you try to recover to that point and try to push execution forward from there on. While sagas have as a main goal that if something goes wrong, you try to roll back what you did to get back to a consistent state and then maybe try again or not, depending on what your business logic is there. So how does that relate together? So by default, what you would want to do is push execution forward, and only in certain cases where your business logic demands it, you could decide, I don't want to retry this, I actually just want to roll back to a consistent state where I was at the beginning and just forget about this. So durable execution is actually something that works nicely together with sagas, because rolling back becomes another form of pushing the execution forward. So with durable execution, the way you can implement sagas is by just keeping a list of what you want to undo. So here is the same example of the payments. I generate my UUID, I create a recurring payment, and then the subscriptions. And so what do I do now in order to roll this back if there's something that I don't want to retry is I add a compensating action to my list. And this will be deterministic on retries as well. So this list will then be all the actions I need to undo in my catch block. So here I catch an exception called terminal exception, which is a name for an exception that I don't want to retry. So the way you tell restate to not retry is just throwing a terminal exception, and then it runs these compensations in reverse order in this case. And so you have the guarantee here that all compensations will be run no matter what, and if something there goes wrong, it will be retried. So let's try that out. Now I'll just send my request via curl because it's a bit easier. So I will send a request here to restate because that's who will proxy it. I want to send it to my subscription saga, which is just the name of my service here. And I will send it to the method called add, which is the name there. So I will do the same, a credit card, a set of subscriptions, and a user ID. And if I execute this, it will hit my last breakpoint here, which gives me a second to show what it actually did. So if we go here again to the UI to see what it did, we see that, so it's running, so it's stuck on that breakpoint. And if we go to see more information about it, then we see that it created the payment, then it subscribed to these services, then it tried to do the Disney subscription, which had the error that that's not available in this region. So that's a reason to say you cannot create this recurring payment, because otherwise this user will be paying for something that they can't use. So roll everything back and ask the user to do something else. So then you see the different steps of removing everything again. And now if we move this breakpoint, then and we refresh this, then okay, invocation is not found because it has been removed. Oh. I need to zoom out a bit, so close. And if I now refresh it, you see that it's not there anymore. So that's how sagas relate to durable execution, and a bit how like these kind of workflows work and what you can use it for. But everything I did until now was pretty boring. It's just wrapping the functions in ctx.run. So let's have a look at some other things you can actually do with this same mechanism. So the next thing I'll show is about concurrent async tasks and about racing futures against each other. So imagine the use case where you sign up to some online service and they tell you open up your email and click on the link to verify your email address. A way this could be implemented is by here generating some ID and a link. We send an email and then we wait for the user to click this email. So the way we implement this here is by ctx.awakeable, which is actually a durable future. So a future in Java is not durable in the sense that it lives in your JVM. If your JVM crashes, you lose this future as well. It's not something persisted anywhere. So with durable execution, you can have a future as just another line in the log, and you can recover it anywhere you want on another process, in another moment, like tomorrow or in 1 year. It's like it's a persisted thing. So the example here, what it does is you have this durable future where we wait on a user to click the link, and then we have two timeouts. One is a verification timeout, so we give the user 24 hours to click this link. After that, it's not valid anymore. And the second one is to send a few reminders. So you could imagine that this should be hours in real life. You don't want to send a reminder every 10 seconds, but it makes the demo a bit more interesting. But so this works well for these kind of like long running processes which take maybe a day, maybe even longer, weeks, and where you want to be able to recover this after restarts or failures. So the way you can raise them against each other is by the select statement. I wait for either of these to complete, and depending on which one completes, I either return that it got verified, rejected, or I send a reminder and wait again. Or I just throw a terminal exception that this is the end of my attempt and that this didn't get verified. So I will run this example. I will send here a request to my email verification service to verify my email, and then if I run this, it gets stuck on me clicking the link. So if we look at the logs, you see that it sent an email to me, and in order to resolve this, I need to click this link. See that here it already sent the first reminder after this 10-second timeout. So just for visualization purposes, we can have again a look at what this looks like here. So we see that we send the email, then we see the sleeps getting raced against each other. So this is the long-running sleep for the verification in general. And then you see the reminders being sent every 10 seconds. So if I now actually execute this curl command, then I'm doing the same principle as resolving this future, and this will have disappeared. So that's the idea. If I what I actually wanted to do is make the service crash before resolving it, and what you would then see is that this the resolving of this future would also be persisted, and when I bring the service back up, it just gets the information that this future got resolved in the meantime, and it will continue from there on. So we've talked a bit about sagas and workflows and timers. There's more you can do with timers that is quite nice and easy to implement. Here is an example of a claim processor, so insurance claims. So I have here a method called submit, which takes an insurance claim, and then it interacts with some legacy systems. So first it creates a claim somewhere, and then it waits for that system to finally have done the pre-approval. So I'm calling a get status method somewhere there and sleeping until this gets approved. And then when it gets approved, I update another system. So it's a bit like a transaction where I first want to do one thing, then wait for X amount of time, you don't know how long that will be, and then update another system. And the thing I want to show here is that actually any of these things can also be connected to Kafka. So I don't know if anyone here uses Apache Kafka somewhere in their infrastructure. Okay, quite a few. So the way you would usually read data from Kafka is either via a Kafka consumer or use a system like, for example, Flink or Kafka Streams. And if you look at how you implement a Kafka consumer, what you do is you pull a batch of messages from the queue. You get like a list of messages back, and then you loop over those messages and process them one after the other. And Kafka as a system has partitions. So you read from a specific partition, and you get the batch from that specific partition. But a single partition can contain multiple keys. So data gets partitioned and multiple keys can end up on the same partition. And when I get a batch, it contains data with different keys. And so one of the problems you have in this kind of applications when reading from Kafka is that if I do this inside a loop, any long-running process will block my loop. So I would need to find another way of executing this somewhere else, because otherwise reading the next event will be blocked on my claim here being pre-approved. So what restate does is it reads from the queue and it lets you just scale out the execution of all these things in parallel. So I think I still have a Kafka cluster running here if I have a look. Yeah, so I have a Kafka cluster running with a single broker. And now I will tell restate where it can find this cluster and to where it needs to send the data. So the claims topic, which is my Kafka topic, will have all events forwarded to the claim processor / submit, which is this function here. So if I execute this, this now creates that subscription. And as you see, I don't need to implement like a Kafka consumer here, because that happens on the restate side and events will get pushed. So this doesn't work in a pool base, but events get pushed here. So let's publish a few events to this topic. So here I will publish for 2 different users, different issues that they experienced for insurance claims. And I will use a Kafka console producer to put them on my claims topic. So if we execute this, what we see then in the log is that these different claims are getting processed in parallel. So my first claim for user 1 and for user 2 are getting processed in parallel now, whereas if they would be on the same partition and I would be processing message after message, they would be processed sequentially. So this is like the same as a queue per key. And these long-running processes, if I restart this somewhere halfway through, this will just continue exactly where it was at that point of the execution. Yeah, so it will just start the pre-approval again, waiting on it instead of asking to do it again. All right, then let's go over to the last example, which adds one more feature or problem to the statement here. So that is keeping state in applications, so writing stateful entities. Things like state machines or durable actors or agents, or also things like what I have here, which is a package tracker. So what I want to do is I want to have a state machine of my delivery. I have one method called register package, which lets me store some data in a key value state. So this key value state now doesn't live in a key value store, but it's just another thing I do in my code. So it just becomes another line in my log. A state update is not anymore a different system that I'm talking to. It's 100% consistent with where code is. So you cannot get into situations where your state is inconsistent with what your code is actually doing right now. So after a crash, it will know whether or not the state got changed, and it will set it again to the same thing. So I have here 2 functions. Update location will get data over Kafka and will update that same package info object in my state store. So this is effectively a join between RPC requests and Kafka events. So I can register the package that has as its final destination Amsterdam. This is like an RPC request via curl. And then the next thing I do is I just send some messages to my Kafka topic to say where the package is right now. So this is just time of where it was and the location. And after I execute this, I can expose this state to other interested parties in this, and they can call here like another handler to retrieve that state again. So maybe a dashboard where I want to visualize for my user what is the current status of this package. So if I call this get package info, I get this state back. And one last thing there is that you can also just request what the state is from the UI and see where right now this package is. So that's a bit the main features that, or the main demos that I wanted to show. So let's go back to the slides. So I started the presentation with this slide of like all sorts of problems that can happen in applications in general. And so actually these kind of issues can be solved by durable execution as a concept, which takes away a lot of complexity in systems that we have now. So if we have a bit closer look, things like half-executed orchestration or distributed transactions gets helped by logging what has been done and not making sure that you don't do it again. Things like timeouts, where you can use retries. Duplicate requests is an example of idempotency. So if you add an idempotency header to a request, it automatically duplicates them to avoid that you process the same request twice. Things like zombie processes and network partitions are not an issue anymore because the ground truth of what your application does lives within Restate as a database. And if a system is cut off and cannot send progress updates anymore to the central server, then it will get cut off and it will be stopped from making progress. Corrupted state, as well as I showed in the last example, and problems like race conditions and concurrency. So what does this server actually looks like? So it's a single binary written in Rust, so you don't need to have extra databases and queues next to it. You can run it in a distributed way with snapshots to S3, and it lets you do cloud native failover support. It's open source, so you can just go to docs.restate.dev and try it out for yourself. So a bit about the internals. What does it look like? In some way, it's like a transactional stateful stream processing engine. So what do I mean with that? You have like 2 entry points for events, either clients coming from the outside or updates coming from the service itself. And what's inside the box is basically a big event loop, which either takes events coming from the ingress, so from the outside, adding them to the log. And the event loop then just looks at the event, and based on what it is, does something else. If it's a call to another system, it does the call. If it's the setting of a timer, it stores the timer. If it's updating state, it stores it in RocksDB, etc. So that's a bit how this works. So from a bit a higher perspective, it's a distributed system in which the primary durability is storing snapshots to S3. The most recent events are replicated between the different Restate servers for like the durability in short periods of time. You can deploy services anywhere you want, so it doesn't require you to run on some specific type of worker. It can just be a JVM in a pod on Kubernetes or an AWS Lambda function, as long as it can be talked to via HTTP. So we currently have 6 SDKs: TypeScript, Java, Kotlin, Python, Go, and Rust. So different type of applications can benefit from different languages there. So these are currently the supported ones. The community of Restate currently uses it for mostly these use cases. So I showed quite some of them, like the sagas, event processing, distributed transactions, but also in general things like payment processing or types of use cases where you need high correctness and where you want things to be resilient. And then 2 also interesting ones are things like AI agents or workflow interpreters, because the big difference between durable execution and workflows as we traditionally know them is that most of traditional workflow orchestrators let you define a static DAG, and basically events get pushed through this DAG. What Restate does is every event builds up its own recovery log. So there's no static definition of what that event can do. It can go anywhere where it wants. So in the case of AI agents, the agent could decide to let it go to one tool execution to another one, and it will just be a new line in the log, whatever decision it took. The final type of use cases which may be interesting is control plane. So any use case where you have a lot of retries, long-running processes which retry a lot until it finally succeeds, these kind of things. So that was it. I hope you enjoyed it. If you have questions, I will have a look if someone asks any there. And otherwise, you can scan the QR code and check out the project. We have a Slack and Discord server community channel where we are super active. If you have any questions, you can always show up there. What if the restate server dies? So restate is a distributed system, so you can deploy several instances of it. So in most cases, never dies completely because the other instances would still be there. If it loses the majority of the servers and isn't able to make consensus anymore, then it will just block there. But so in a distributed setup or a multi-region setup, you shouldn't run into this situation too often. So yes, it has a consensus algorithm at its core, and based on that consensus algorithm, it replicates events to the other servers that are running. What happens if there is an error with the execution of the rollback of the saga? So the same happens as if there is an error with any other part of the execution. So it will just keep on retrying that specific step in the rollback until it eventually succeeds, and it will keep retrying forever with exponential backoff. How will the reference to the already executed steps work if there was a change in the code? So that's like a common question, is how to do versioning in combination with this. So the way that we approach that is that we assume a endpoint is immutable. So if you want to deploy a new version, you deploy it with /v2, for example. You register it again, and then Restate will send all new invocations to the latest version. All existing invocations will go to the previous version. And so you need to keep the previous version around for as long as there are still invocations running on it. We have tooling which lets you see which deployments got drained. So if you go here in the UI, you can actually see which deployment is currently answering invocations here, and you could see different versions here, and then you can actually also go to this deployment and delete it when you see that it's drained. So you can also see in the invocations tab, you can like filter on deployment ID, check which one is still having invocations, and when it's drained, you can remove it, and then all requests will be processing on the newer one. But so one thing to keep in mind there is that if you have very long running processes, it's always preferable if you're able to split them up in multiple shorter tasks to make versioning a bit easier and not need to keep services around for months. How old is the Restate technology? So Restate is developed by the same people that were behind Apache Flink. So they saw Apache Flink being used sometimes mainly for like its fault tolerance characteristics, but actually Flink is not a system which covers these kind of use cases. Flink is like a big data analytics tool where you actually also define a bit like a DAG in code, and you push events through them and calculate things like windows over streaming data. They don't fit well for this kind of more transactional use cases where I want to update one system, then update another, then wait for an hour and then do something else. Because Flink does not, for example, have durable side effects. So you don't get any guarantees on the side effects, only on the end-to-end execution. How old is Restate? So Restate is around 3 years old, but it came out of Flink, project called Stateful Functions they did there, and they used Stateful Functions as like a first POC version, but it was bolted on top of Flink and didn't fully nail everything. So they started a new project called Restate, which actually nails this kind of use cases for either event processing or for just general RPC services. So it's around 3 years. The big launch was now 1.5 years ago, I think. I think that's it. What happens when the request to the other system is successful but the program crashes before sending it to Restate? Yeah, so when you look at the code that I showed, if I do something like a payment, the way usually these APIs work is either I generate an ID myself, and this ID is then persisted and is then used here to let the other system deduplicate them. For example, Stripe allows adding an idempotency key. Many APIs allow adding some kind of idempotency key. And so what you can do is you have an idempotency key which is 100% stable across retries, and then just use it with confidence. The other type of APIs that exist is where you first create like some kind of proposal of what you want to do and then commit it, a bit like two-phase commit. For example, reserving a car, this kind of APIs often work like that. First you create the proposal and then you say, okay, confirm this. So in that case, you also have these two different steps which let you make that durable. What are the advantages over workflow engines like Camunda? So there are like few other options like Camunda. There's also temporal. So I would say like one of the cool things about Restate is that you just implement services in an RPC style. You don't actually implement workflows. You have a service with a set of handlers, RPC handlers, and they can be called over HTTP. And this lets you stay a bit closer to the way you would normally implement these kind of services if you wouldn't use the workflow paradigm. So it actually just turns functions in your infrastructure into workflows. And one of the advantages here is that it's lower latency because we work in a push-based way and it's more event-driven implementation. So it's changes a bit the idea of having workflows which are very slow. Like most workflow systems don't have many guarantees about when exactly your workflow starts running. It can also take like 500 milliseconds or something. Another thing is that many of these systems also are not a single binary, so they often require you to run the workflow orchestrator system and some persistent database next to it. Sometimes this is Cassandra, sometimes Postgres, like depends on which one you use. But so that's a bit in general how it would relate to each other. Specifically, Camunda is BPMN-like, so it also puts a bit of restrictions on what you can actually do, whereas if your recovery log is just a set of entries below each other, you don't have any like restrictions on cycles in there and taking different forks. It's a bit more like flexible. I think I answered all the questions. How can we configure access permissions to the Restate UI? I guess that depends a bit on how it's deployed and everything. I think if you're really interested in that, might be best to ask in our Slack or Discord channel, because I guess you would use the same mechanism that you use for other UIs that you have. Okay. Thank you. If there are any other questions, you can always come to me.